everybody, and a hearty welcome to each one of you tuning in from various locations. I'm Monal, delighted to be your host for the second installment of our eagerly awaited Kate Smashers Bootcamp series. Today, we mark our second day of exploration into the world of technology where we are set to break barriers and expand our knowledge beyond together. Leading us through this expedition is none other than Siddhant Khisty, a true expert in the realm of networking. Before passing the stage to Siddhant, I would urge everyone to actively participate, pose questions, and interact with the material. Remember, curiosity fuels learning. So, without any further delay, let's extend a warm virtual welcome to Siddhant Khisty. Siddhant, the stage is over to you.
Thanks for that intro, Monal. Um, hey everyone, I'm Siddhant. I'm a developer advocate at Siglance. I am also one of the organizers at CNCG Nasik. And I wouldn't say that we have similar events, but we do try our own parts with virtual events as well. Looking forward to today. Now, before go ahead and share my screen and we get started with all networking shenanigans, I'm going to be upfront and honest with everyone. I have not prepared anything for this session. So this is going to be completely free flow. I've just listed down a couple of bullet points on my screen. And if you feel like there's something else which we can talk about apart from the bullet points which I've mentioned, then we can talk about that as well. And yeah, if anybody at any point wants to come up on stage and have it in an entire discussion based approach, feel free to do that because that will help me as well and it'll help you as well. And again, since I said that I don't have a proper flow ready, this is a very last minute flow which I've created. Some things might really not make any sense to you. So in that case, feel free to ask about it. Don't worry about it being a stupid question or anything of the sort. Alright then, with that being said, let's get started. A bit about what all things I want to cover, and obviously we'll add more stuff onto this list as well. But first, I want to give you a general idea about networking without talking about networking. After I finish this part, then we'll go ahead and talk about a little more technicalities. How does it actually work? How do networks work today? I can't like give you a taste of networks because let's be honest, everybody here is already experiencing networks. If you're in this call, you already have a taste of what networking is and how it works. Then just some key concepts we'll discuss over here. We'll talk about ports, we'll talk about IP addresses, we'll talk about IPv version 4 and version 6. After that, we'll talk about physical devices and their entire role within the network landscape. Just a few important ones which I've mentioned here. There are more than this as well, but just to understand about the basics, these much are more than enough. Then we'll talk a little bit about the OSI model as well. I'll just give you a brief introduction to the OSI model because I think that having more hands-on approach to this will be a better way to understand it. Talk about the HTTP protocol as well. That's like the most popular thing you can have today. And then TCP, UDP, and DNS, all this fun stuff as well. All right, so getting started with giving you a general idea about networking. Now, Shubham already said that we are connected via network. That's not entirely false, and that's pretty true, to be honest. But just as a general sense, when we were all kids, do you folks remember that one thing we used to do? We used to take two cups, tie a string at the end of it, give one cup to our friend, and we used to go at a like quite a long distance. Even if we shouted, your friend would never actually be able to hear that you're shouting and try to say something, right? But instead, if you spoke into the cup and your friend had the cup on his ear, they'd be able to hear you, right? Does anyone remember that game? Let me know down in the chat. That was pretty popular, at least when I was growing up. All right, then Gaurav remembers it. I'm sorry, I can't pronounce that. I haven't watched anime in a long time. All right, so that game is basically what networking is. You're just, let's say that this is your friend at one side of the world, and you're here at another side of the world. You don't have any way to connect with your friend here, but instead you bring in this whole concept of paper cup and a string, and using that you're able to connect with your friend who's at a very big distance. This is basically how it is with modern networking as well. All this networking which we do to go to something like YouTube, to use Twitter, it's the same general concept, just it's a lot more advanced than a simple paper cup and string. Then next thing is, how does networking work exactly? I gave you the example of the paper cup and string, right? That is pretty much the exact way in which networking works IRL, in real life as well. In order to understand a little bit better, let me first go ahead and talk about the physical devices. So first thing to know is, okay, let's just abandon this flow for a little while. So in every single city, you have something called as an ISP, an internet service provider, right? Odin, can you not hear me speak? Maybe you could try rejoining. Okay, while those entire problems get resolved, I was saying, in every single city, you have an ISP, all right? Let's say that this ISP exists in a city called City 1. Now, the same ISP will exist in multiple different cities as well. Let's just call these as City 2 and City 3. All right, cool. So, ISP in City 1 is going to handle about how the networks within this City 1 are handled. So, you have tiny houses in one city, right? Uh, All of those tiny houses, let's just visualize them. Let's take 3 houses over here. Now, in order for these 3 houses to be connected to the entire world, for example, to City 3 and City 2 and City 3, they will first need to be connected to your core ISP. Before we go ahead and talk about core ISP, let's come one level lower. So that is within the city. Now you have these 3 houses in the city. Let's just assume that they are very far away. So they are not neighbors. So if they wanted to talk to each other, they can't exactly just get out of their house, walk to the second house and say, hey, hi, I'm your neighbor. I want to talk about this and this thing, right? You've got phones for that. We're not talking about phones here, but if these people wanted to talk to each other, they would need to be connected, right? Now let's take our example of the cup and string again. There would need to be some way to connect these 2 houses together. Now these 2 houses can talk, but this third house still cannot talk to either of these two. So both of these houses are going to have to connect to this third house as well, right? Now, if there was another house which was built somewhere later on, there's a completely third house. Now, all of these houses are going to have to be connected to the fourth house, right? Now, this is how all of these houses are able to talk to each other. They're connected in some sort of way, either by the cup and string method or with more modern methods, which we'll take a look at a little later. Now, if all of these houses, let's say the same exact grid of networks, exists within city 2 as well, and somewhere far away in your third city as well. Now, this entire group cannot talk to this entire group, right? Again, if you wanted to talk, you would have to establish micro networks this way. Now, if you try to do those kind of micro networks, it's going to become very costly. Those cables which you use for connecting all of these devices together, these different computers and networks together, they are expensive. They're not cheap, right? So instead, what you will do is you will connect to this ISP. So every single device in here will be connected to an ISP. Let's just go ahead and create that connection. Okay, cool. Now this ISP will be connected to the ISP in city number 2. And city number 2 will have a similar scenario where all of these networks are linked to your ISP. Make sense? That makes the entire citywide communications possible. Cool. Now let's go ahead and talk about a bit about how a lot of physical devices come into play. Now for now, just forget about these ISPs. We're going to talk about something a lot more local. Let's say you have a house. This is your house. And inside that you have multiple computers. You can have phones and all as well, but just to keep the concept simple, we're going to stick with computers. Let's say multiple computers, one over here, one over here. Let's take 4 just so that we have enough computers for an example. Once again, the same concept which we said over here. All the networks, all the houses will have to be connected with each other to talk with each other. That same thing applies here. But I talked to you about cables, right? Like there's that connecting material. That thing is quite expensive to source as well. So instead, you don't want to go ahead and connect everything individually. So this connects to this, the same thing connects to this, and then same thing for every other thing. Becomes very expensive, becomes very tedious as well. So instead, you have a physical device over here called as a switch. Let me just see if I can find a image of a switch on Google real quick. Then I can show that to you as well. Cool. Found a nice image. Let me open this up. Shubham has put in a pretty nice diagram. And once I'm done explaining all the physical devices I want to, I will talk about that diagram as well. Thanks for the diagram, by the way, Shubham. So this over here is what we call as a switch. You see these tiny things over here, right? Let me zoom in. All right, these things over here. These are what we called as Ethernet ports. If you look for the technical terms, they are called as RJ45 ports. Okay. This is where you will plug in your cables. And what exactly happens after you plug the cables into the switch? The cables which you plug into the switch are going to be from all of these devices, right? So this device connects, this connects, same with this. And just so it's easier to talk about this, let's give every single device a name. Call this A, B, C, and D. Okay, so instead of device A connecting to B, C, and D with just one network, and then B doing the exact same thing, C doing the exact same thing, and creating just a mess, frankly speaking, a mess of wires, a mess of cables, we connect everything to this one central device called a switch. Now this switch is able to connect device A to device D to C and B and vice versa. And here we're using only 4 cables as opposed to connecting this, all of these things individually. Right. Wi-Fi routers also have 3 or 4 port switches built in. We'll come to that a little later. Yes, that's absolutely right, but a slightly misleading. Talk about that in just a second when I talk about routers. This is basically what a switch is, all right? Now this exact same thing, let's say it exists in a second house over here. Now even if I tried connecting this switch in house, let's call this house 1 and this is house 2. If I tried connecting the switch in house 1 to house 2, it's not going to work. There's a concept called as routing tables, which I'll talk about a little later. But basically, this entire connection, switch to switch, is not going to work. So if I want that whole thing to work, I need to introduce another new device. Now this device is going to be a router. Okay. Let me just quickly try and find another image of a router. Mm-mm. Let's use this. This image of a router is what you all might be most familiar with. So this thing, if you have internet in your house and you have proper Wi-Fi, your internet connection is coming from a proper ISP, then you're probably familiar with a device that looks like this. This is basically your router. This is how you're going to connect to different networks outside your own network. So it's right here. The network which is inside this house is one network. The network inside house 2 is a second network. Right? Switch to switch communication doesn't work. We already established that. So if you want to make that entire communication, your switch is first going to have to be connected to a router. Now this router will then be connected to a router which exists within the second network as well. So here as well there will be a router which will be connected to the switch of the second network. And then the routers will be able to talk with each other. Make sense? This is how the entire communication works. Now, why does switch to switch communication doesn't work? That's where your entire concept of a routing table comes in. Before talking about routing tables, we need to talk about IP addresses. Now, this might get slightly confusing, and if it does, if IP addresses start getting confusing, either request to speak on stage, come up on stage and help me explain it as well. So you ask your queries and I try it and solve it, or feel free to drop that down in the chat. So this switch, how does it know where is device A? How does it know where is device B? How does it know where is device C, and so on? Every single device has its own address, and that is what we call as an IP address. Usually it is something like this: 168.192.168.1.10, let's say. Similarly, this has a different IP address. Let's keep it 11. This has a separate IP address. This will be 13. And another one over here, 14. Your switch as well will have an IP address. Let's give this 1.1. And the router is also going to have an IP address. The router is actually going to have two IP addresses. One will be 1.0. And the second IP address, I'll talk about it a little later. Right here, all of these devices have some sort of an IP address. Let me just put this over here. Okay. All these devices have IP addresses. That's how they know how to communicate with each other. If device A wants to talk to device C, it's going to say that, hey, I want to talk to a device which has the IP address 192.168.1.13. Okay. Then it will send that message to the switch. Then the switch will say, okay, yeah, this device is connected to me. Here's this device. Let me establish the connection for you. That's how the whole communication happens. Same thing with the router. Before coming to the router, the switch has an IP address of 1.1 because your switch is basically acting as an access point, right? Switch is basically the central place in your house which all the other devices are talking with. After it talks with the switch, then it goes to the router. Now the router has something called as a gateway. Why is it called a gateway? Because it's basically acting like a gateway, right? The router is enabling you to talk to Am I still in the call? Okay. My screen just flickered, so thought it's a bug. Uh, all right. I was saying,
There.
yeah, I'm here, right?
Yeah.
All right, cool. So I was saying the router is what enables you to talk to all networks outside your own private, your home network, right? So it basically acts like a gateway. You have to pass through the router in order to access the rest of the world. So that's why the router is called as a gateway. Now, a little bit earlier, I said that a router has got two IP addresses, right? That's where the whole concept of private networks versus public networks comes into play. Now, this whole networks series here, this 192.168.1.13, this whole thing is a private network. This exact same IP address of numbers can exist within the networks that is in house 2 as well. Why? Because it is private. Nobody is going to be able to talk to these particular IP addresses if they exist outside this network. Now the second IP address which your router will have is something like let's say 231.147.82.95. It could be something like this. And then this other network here could have something completely different. It might be 131.177.82.95, which is once again a completely unique IP address, right? So when we come into the area of public networks, your router is going to see that this is the IP address that this router has, and it has to communicate the data to this other router which has this weird IP address. In order to find that IP address, the router has something called as a routing table. In order to understand that routing table, let me show you a different diagram. Let this stay as it is. We'll come back to that later. So there are a bunch of routers which we have here. Let's keep 5 routers for the sake of simplicity. Again, naming them as A, B, C, D, and E. All right. Now let's say router D wants to talk to router A. Some computer within the network that's connected to router D is saying that I want to send data to somebody connected onto router A. How is router D going to find how to get to router A? So that's where we have a routing table. If I can find an image of a routing table, something that actually makes sense. Okay, never mind. There's no good image of a routing table. If someone can find a good image of a routing table which isn't just numbers, please do drop it in the chat. We can use that to better understand this concept. So every single router has its own routing table, right? This routing table is basically going to be a list of addresses on this router exists here, this another router exists here, this third router exists here, right? So that entire list could be static, which means it doesn't change. But a static routing table is kind of useless in today's modern world because things keep changing so much. So instead, there's a dynamic IP address. A dynamic routing table. How does that work? Now, router D is going to have its own static list, right, of IP addresses. So let's say it has a router number C within itself. So first router D will go to router C and say, hey, I have to reach an endpoint of router A. Do you know how I can go there? Then router C can be like, I don't know exactly how to go there, but I have router E and I have router B connected to me. They might know how to go there. So router C tells router D that one of the closest ways to reach router A is via router E. So router D will first go to C, then E, then the same process will happen in E. E will figure out which routers are connected to it and figure out the closest path to get to router A. And then router E will say, hey, just go to router A. I am the closest way to get to router A. So you see, router D is not directly communicating to router A or destination A. It's hopping through a multiple different routers. Now, if this is within your city itself, this doesn't make much sense to do, right? But now imagine that this is different countries. Let's say, let's take an actual example. Let's say this is router D is some router in India. Router C is some router existing in, let's say, Indonesia, because in terms of routing, Indonesia gives the best connectivity speed. And A is A, your destination A is basically, let's say, Australia, for example. Australia. And E can be a country like, um, I don't know if this makes geographical sense or not, but let's say this is a country like Malaysia. Okay. So my end destination is somebody who's staying in Australia. I can't directly hop there because the distance is far too great. If I try to do that, the speed is going to be super slow. And besides, I don't even know how to get to Australia. So instead, I will go to Indonesia. I know how to get to Indonesia. From there, I'll figure my way out. Indonesia tells me that go over to this router in Malaysia. Then Malaysia tells me, here's my final destination. Here's how I finally reach it. So you do a similar thing when you try to find some place in your city, right? When you are not using Google Maps, you'll go to person. You know how to get to one street in your city. Let's say, um, what is some good example street name? Let's just call it example street. You know how to reach example street, but your destination is something like, Rajiv Gandhi Street or something similar, right? So you come to example street, you ask somebody how to get to this Rajiv Gandhi Street. They point you to some other place. At that other place, you ask somebody else, and they finally tell you how to get to Rajiv Gandhi Street, right? That's how you do it in real life when you have to go to some sort of place you don't know how to do it. The exact same way works in networking as well. This whole concept works with routing tables. So these routers have its own routing tables. These routing tables is how it knows how to get to the second destination IP. Okay, makes sense. Now let's talk about the diagram which Shubham shared. About the diagram that Shubham shared. This is basically what I just explained to you, right? Like you have a couple of devices in your home network. They are connected to a switch. Your switch is connected to a router, and the router is then going out into the wide world, into the rest of the world outside your home, right? Now this one layer of firewall, I'm going to ignore this one for now because that's a little, we'll understand that a little bit later after we understand IP addresses properly. Modems, I don't think modems are still used in the modern world, but in the past, modems were a very big thing. Modems used to, the entire communication to the outside world, to your internet service provider, your ISP, that used to happen through modems. So it used to be a switch, modem, and then the whole internet. I don't think there was a router in the picture back then. Treat a modem as an ISP, that works. So instead of modem, just think that this is your internet service provider. Internet service provider will exist within your city, and then that ISP will be connected with multiple other ISPs in your, either in the same city or across multiple cities, which then in turn are connected to ISPs across the entire world. And that's how the entire world's networks are formed. Okay, so in this diagram, just treat the modem as your ISP. And yeah, your router can also be wireless. So everyone knows what's Wi-Fi, right? Routers have that capability as well. Now this is your router over here. Let me talk about the ports a little bit. These gray ports ignore. These red ones are what allow you to make a connection to different devices. A little earlier, Sayan mentioned that routers have their own switching capability as well, right? Which is true. Most of the routers which you get for home usage have are basically a router plus switch. This blue cable which you see, this is what's coming from the ISP. That's what you plug into the to your router, and then your router is capable of providing an internet connection which can connect to the rest of the world. Now if you want to connect this router to your computer or other physical devices, you'll plug your cables into these red ports. These are called as your LAN port, and this blue color port which takes the internet connection coming from your ISP, that's called as your WAN port or WLAN port, wide area LAN. LAN basically means local area network. And this is your switch, right? Switch is basically the same thing as a router. Not basically the same thing, its capabilities are different, but its ports are the same. This is an industrial grade switch, which is why you've got so many ports. I think this has a total of 32 ports on it, if I'm not mistaken. But in servers, in data centers, you have that many devices as well. So you have all these different ports in that. And this router is again meant for home use. In home use, you don't have that many devices unless you're a very janky networking person like me, or maybe like Sayan or some of the other folks in the audience. In that case, you need more networks. So in that case, you'll connect one of these LAN ports to a switch, and that gives you access to a lot more ports and connectivities. Now, if let me see if I can find an industrial grade router. And what do you know? We're in luck. I found one of those industrial grade ones. Let me just get that here. So this is one of those industrial grade routers which I talked about earlier. This one is from Cisco. Cisco, as you know, is one of the very popular networking companies. In here itself, I haven't worked with these, so some of my things might be wrong. But these 4 slots which you can see here, let me try and highlight this a little. These 4 horizontal slots, I believe these are acting as your internet uplink. So this is where the internet will actually go. And these on the left here, I believe they act as switches. I might be wrong over here. I've never worked with one of these bad boys, so not entirely sure. Hi, this switch is integrated with the CPU, right? Omi, this actually depends on what you call as a CPU. If you refer to, let's see, if you refer to this big box as a CPU, then you're correct. If you refer to this chip as your CPU, then you're wrong. So what are you referring to as a CPU? Yep. Okay, I'm going to go on a bit of a rant here. For the love of God, this thing is called as a computer, not as a CPU. This chip is what's called as a CPU. Anyway, technicalities. Let's not concern ourselves with those. Cabinet, yes. Thank you, Ronit. This chip right here is what's your CPU. I really get annoyed and triggered every time somebody calls this big box as a CPU. We were taught wrong terms. Indeed, this is one of the reasons I hate the education system. They literally tell you this box is a CPU, which is absolutely wrong. All right, enough ranting. Let's come back. What were we talking about? Routers and switches. Is the concept of routers and switches clear to everyone? Let me know down in the chat. One little question. Go ahead, Omi. I hope I'm pronouncing that correctly. Either come up on stage or you can ask in the chat itself. What does ISP do? Good question. Let's come back to Excalibur. Let me go back here. This whole thing, right? Imagine that these are IS. This thing is a whole ISP thing, right? One second. Let me just see how I want to structure explaining this. Okay. Everything is connected by wires. That much part is clear, right? So ISPs are basically going to help you communicate with different cities. Now, where's that one diagram? Here. You have all of these different networks within your city, right? Now, I'm going to just delete these individual connections and instead just have these connected to ISPs. Over here, the ISP is basically acting as a switch for within the city. Okay, within the city, your ISP is comparatively acting as a switch. Now, if you want to talk to outside your city, to some other city, let's say city one is my diagrams. Let's say city one is Delhi, city two is, let's say, Kolkata. You can't form this direct connection between the ISP itself to this other city as well, right? That would be way too expensive in terms of your cables and everything. And also, it would just be an inefficient way. So instead, your ISP, which exists in Delhi, will be connected by wires to an ISP existing in Kolkata. Both these ISP will have their own routing tables. Now, this Kolkata ISP will again be connected to all of these devices which exist in Kolkata. Does that make sense? Ami, let me know if that makes sense. Others in the chat as well, if that makes sense, let me know. All right, cool. You folks want to keep going ahead or you want to take a small little break?
I think we can move forward
Okay,
because
then.
we took a break which was not expected.
It's a 2 hour long thing. If it's not break, then people are not going to understand anything. That's just how the brain works.
Yep.
All right, then let's go forward.
Yep. Have some sip of coffee and move forward. Yeah.
If I drink coffee so late at night, I'm not going to sleep.
Okay.
Okay.
Now ask more. Yeah.
One thing I want to cover, hubs. Hubs basically acts as a switch, but the only difference is if A wants to talk to C, through a hub, D and B are also going to be able to listen to it. Okay. If you use a switch, then only A and C are going to listen to the message. If you use a hub, everybody on the network will use a message. That's just one thing. Cat5 cables. Yes, let's come to this. Cat5 cables are fun. So you know these cables which connect to your routers, right? Those cables are called as cat cable. Now there are many types of cat cables. They just go from cat 3, cat 4, cat 5, cat 6, cat 7 all the way up till cat 8. The only difference between the numbers is how fast can they transfer the data. So this cable which you can see here, that's your cat cable. And this connector which you see at the end over here, that's what we call as an RJ45. Now this is going a little too in depth, but inside every single cat cable you have these few wires. These wires are how you're able to communicate with different devices. Some of these have incoming signals, which mean they tell that this data packet or this electric signal is an incoming flow. Some of it say that it's an outgoing flow. Some of these pairs do both, and so on. Some are just for speed. Okay, that's the beauty of Cat5. Pin is RJ45 and cable is Cat. Exactly. Okay, what the hell are those medicines? This one. See this cable over here, this white color cable? That's the RJ, that's the Cat cable. And this end connector here, this plastic thing which you see, that's the RJ45. Let me just show you what's an RJ45. I have my entire RJ45 kit as well, but I think it's in my cupboard somewhere. This entire connector is what's called as an RJ45. Color codes. I still play around with those color codes, to be honest. Every time I have like 100-meter long Cat 6 cable, I think. And every time I want to make a new connection to my router to some new device, maybe I found an old computer which I'm using as a server, I literally have to crimp that with my RJ45s. This cable is used to connect from router to computer. Yes, it's used to connect from your router to your computer, or it can be computer to computer. Basically, to connect any devices through a network, you'll use this cable, this RJ45 cable. Yes, out of Odin is also correct with his explanation of what an internet service provider is. Okay, then this was the entire cat cable. Just as a fun fact, I actually never had this crimping thing in my college. In my college, they just taught us the OSI model, which will be the next thing we talk about here. And that was it. They never showed us any practical about using Linux commands for networking or crimping these cables itself. Oh, that was a question. Sorry about that. Internet, it's sort of as companies. Well, you're right about that as well, Odin. That doesn't feel like a question, to be honest. That just feels like you stating a fact. But yes, internet service provider is the companies as well. Obviously, the companies want some sort of compensation, right, for all the services they are providing. So it is the companies as well. Let me see if I can find the network connectivity map. Is that a diagram? Not this. Um, world map. Can I find some of that? Mm-mm-mm. Yes, not. So there was actually, when I was learning about networkings, there was actually one really nice diagram. Let's see if I can make a half decent representation of it in Xcali. So basically, this block over here was America. Then you had Africa in the middle, Europe somewhere up here, but that I'm not going to show you. I'm not biased against Europeans, FYI. Just lazy to draw out all of those. And then this was Asia. And then that diagram basically showed that over on the US continent, there were a couple of providers. They sent a lot of cables through the oceans. So these cables exist underwater. They go to Africa. In Africa, there is a bunch more routing that happens. And then finally, those cables reach here to our Asian countries, to India and other stuff. I'm teaching better in a few hours than college teaches the entire sem. Shreyo, I don't know if you were here when I mentioned it or not. This whole thing is impromptu. I did not prepare for this at all. This entire where is it gone? This entire small list of things, I literally made this when we were figuring out the initial issues. I'm just hoping that folks are able to understand what I'm saying.
Yes, actually, I have shared the submarine cable link as there. Okay, as
Okay,
well.
yeah.
So appreciate that.
Let's see if I can find this.
Yeah, just you can just
Mm,
search for submarine cables, and it will show you the
submarine
map.
cables.
Submarine cables.
Submarine
Yeah.
cables. Let's go.
Yes.
Okay, nice.
Go for the all. Go for the all, and you will see the
Uh,
map itself. You will get the website.
oh, okay,
Yeah.
nice. This is nice. I didn't know about this one. Submarine cables. Okay, yeah. So the map which I was the badly drawn diagram which was in Excalibur. This is what it actually is like. So yeah, this is like different ISPs which are connecting to different parts of the world. If I can find India on this map, over here you can see that somewhere near the sea area, all these connections are happening, right? One is happening in Mumbai, one is happening in Kochi, another one here. Now, this is connecting to just the entire country as itself, but within the country as well, there are a couple of different things. This is what is called as a tier 1 ISP, which I believe. So, this tier 1 ISP just gives a connection to big companies and between the different gulfs. And within the country, then there is tier 2 and tier 3 ISP. So, from Mumbai, if I wanted to bring it to my city, let's say Nasik, just as a guess, I think it's somewhere over here. That would be via tier 2 or a tier 3 ISP. Somewhere to Pune, which I think is around here. That will again be its own separate section. So over here it's just showing you the underwater cables, I believe. All the cables which run underwater. And in images, if I go, this is what those cables look like. Right, for which. Oh, all right then. I think we've gotten way too off topic. Let's come back to the actual place. And um, what did I want to talk about next? Physical devices done. I think we literally spent an entire hour talking about physical devices. OSI model. Let's talk about this next. Now, instead of drawing it out, let's just use an image from Google. Open a new tab. So the next thing which we talked about, which we want to talk about to understand about networks is the OSI model. Now, whenever you try to, actually Shubham has a much better image of the OSI model. Let's use that. It's got more info as well. Open link. The OSI model. So whenever we want to work with any sort of networks, we are going to talk about the OSI model. So let's say you're an application developer, a backend developer. Some of these concepts you might have already worked with, but I'm still going to touch upon them anyways. I'm considering that someone who's listening to this is a complete noob. So there are two models basically. One is the OSI model, one is the IP model. The IP model is basically the OSI model itself with a lot less layers. So in the OSI model, you can see that there's the application, presentation, session, transport, network, data link, and physical layer, right? Right? This is a total of 7 layers. In the IP model, you have only about 4 or 5 layers, I believe. Let's just check that to be sure. It's 4 layers. IP model. Yeah, it's 4 layers. So basically, your application, presentation, and session layers is one entire layer. They get combined into one single. Transport is another layer. Network is another layer. And your data link and physical layers are again merged. So if you look at this diagram, same thing, right? You have your application layer, which is a merger of this whole application, presentation, and session. There's the transport layer, there's the network layer, and the data link and physical in the network access layer, right? So I'll talk about it from, oh wow, The TCP/IP model is on the screen as well. I need to get my glasses changed. I'm blind. So anyway, I'll talk about the TCP/IP model because that's more hands-on relevant, and that's what you'll do in actual networking. But it's important to know OSI model as well. If you try and work with actual network engineering concepts, right, they'll actually refer to these things as layer 7, layer 4, layer 3. So that's why it's important to know about the OSI model as well. At least the sessions, its different layers. So let's start with the TCP itself. Let's talk about application layer. Application layer, OSI is a theoretical model in no one trying to. Sayan is also right. OSI is again theoretical layer. In actual everyday practice, you're using the TCP/IP model. I'm loving this chat, by the way. If I go silent, it's just me reading the chat. Okay, so the application layer is basically everything that is to do with your application. So I'm on Google Chrome right now. Google Chrome has some sort of code within it. The code then goes and talks to my kernel. The kernel has its own method of talking and translating all these complicated shenanigans into something which is a lot more easier to understand for your physical layer, right? The application layer. Let's stick to the application layer first. Coming back to this, let's talk about ports because ports are important when it comes to the application layer. Now, everybody understands IP addresses, right? Just give me a wave in the comments if you understand IP addresses or not. Okay, a yes to IP addresses. Now, when we talk about ports, we are talking about an individual device. So this whole thing, consider that it is a computer. Now, within your computer, you have multiple applications. Let's say this is Chrome, this is Discord, maybe I have a third application running, maybe I have Spotify running, and somehow from my router, actually wait, let me distance this a little. Let me clean some stuff up here actually. Let's bring this down here. Let's call this Chrome. Let's call this Discord. And another one is Spotify. While I draw this stuff and label it out, what's your favorite Spotify music been this year? Yes, I am biased to Discord, Shreyo. That's true. I love Discord. Okay, then my diagrams are ready. So, an internet connection comes from your router to your computer, right? How does this small little thing know which application to send it to? I have Google Chrome open right now. I have Discord open. How is my router, or rather whatever is acting inside my computer, how is it smart enough to know that data has to be sent to my Google Chrome window or to my Discord window? That's where we have the concept of ports. Now, ports simply mean an opening, right? Do I have the model of switch anywhere? Let's see, switch networking. This one, right? Open a new tab. This switch has these tiny things, right? This is what are ports for the switch. In the same way, you've got software ports as well. I don't know the exact number range, but it's like 1 to around 60, 70,000 something. That's how many ports you have on your applications itself, in your software itself. Now Chrome has some port. Let's, for example, say the port for Chrome is 45213. Let's say another port for Discord is 32564. And Spotify has its own port. Let's forget about Spotify. No one's listening to music right now. So this port number is where all of the data will go. Now, how the data gets transferred, I'll talk about that a little bit later. Let's look at the OSI model real quick. Um, okay, yeah, I think I can talk about it right now itself. But for now, understand that every single application has a port number. Some ports, I think 0 to 80, that is a predefined port range. On that port range, things are already defined. You cannot put your own custom applications on that. Thanks for dropping that down in the chat, Ronit. You have ports from 0 to 65535. Again, this is the tiny sort of information that nobody really remembers or cares to remember, because you can go and Google this. We can't use ports 0 to 80. That is slightly correct, slightly wrong. Ports 0 to 80 are used, but they are reserved ports. Some software or some function is already reserved for those ports. I know that port 80 is reserved for HTTP. So HTTP is a protocol. That protocol runs strictly on port 80. You can custom define it to run on some other port, but this port 80, you cannot run something else on this port. For example, I have a database application running. I cannot run that application on port 80. No, port 80 will stay reserved for HTTP calls. I can define it in such a way that HTTP runs on some other ports, but I can't change what runs on 80. Port 80 will be either HTTP or nothing. Okay, that's the job of this reserved port. Now 0 to 80, it has its own thing. I think there is one page, what are reserved ports used for. I think either on Wikipedia or somewhere. It gives you the entire list of reserved ports. Not sure where exactly, but there is a. Alright, IBM port numbers. Port. Okay, I was a little wrong. It's port 0 to port 1023 which are reserved. Well-known ports are just those reserved ports. Okay, and then 1024 to 65535. This is stuff which you can use, and generally this is how it's reserved. 1024 to 4915 reserved for server side application. So basically server side applications, and 49152 to 6532 reserved for client side. Self-explanatory, right? This port number reserved for things that run on your server, so stuff like Nginx or your Linux instance or something else. And anything else like client-facing app, Google Chrome, for example, Discord, for example, will run somewhere on this port range. Now, I can mix and match these port ranges, but this is just the best practices so that I'm not mixing the wrong things. Sayan has put a nice list of reserved ports. So HTTP on port 80, HTTPS on 443, SSH on port 22, VNC and RDP on those ports. Shreya has shared something. Let's see what this is. This is nice. This is exactly what I was looking for. This is a document which basically tells you what runs on these port numbers. So port 22 has SSH. These protocols run on it. I'll touch on TCP protocol and UDP protocol later on. Is there any other protocol mentioned here? TCP, UDP, SCTP, DCCP. I don't know what SCTP and DCCP are, total honesty. But we'll talk about TCP and UDP. Those are the most common types of protocols. But yeah, if you want to look at all those protocols and servers, if you want to look at the port numbers, what they all have, check this page out, which Shreya has linked. A really nice page. We went off topic again. This is what happens when the sessions are not planned. Where's the thing? Okay. We defined port numbers, packets. That's what I wanted to talk about. Now, how does some data that's coming from your router know that the data has to go to Google Chrome? That is going to be through something called as packets. Now, this data is generated in something called as data packets. All right. Now, let's say that I create some sort of upload. I want to upload data to my Google Drive. In my home Chrome OS, when I click on upload, it's going to create some data packets. So everyone knows that all data in your computer is binary, it's zeros and ones, right? A data packet is the same thing. Data packet is a combination, a packet of zeros and ones. So there's certain numbers of zeros, ones in this with information about your core data as well as the source and destination. So in this case, the source is going to be my Google Chrome at my IP address, and the destination is going to be Google Drive. So it's going to be somewhere at Google servers. Now that information, my kernel will read. Now the kernel has its own processing features and stuff. It'll read that, it'll send it to the router. Router will be like, okay, this is your destination IP. Let me figure out how to get here. This data packet figures out how to get to that particular place where Google Drive exists, and then Google system deciphers this data and stores it in its own hard disks and spaces. Sayan, it's a little too early for trace route. I'm going to do trace route, but yeah, we can do trace route honestly, but let's cover the OSI model first before we go on to the fun hands-on stuff. Where'd my packet go? Did I delete my packet? Okay, there's my packet. Yeah, so this packet figures out how to go to Google server, and this packet is going to have your information. Now, one data packet is quite small, so you have multiple data packets which have your entire stream of data. Imagine I have 1 GB. If I put 1 GB into this thing, the speed is going to be incredibly slow. So that 1 GB might be broken down into, let's say, 50 bytes or maybe 1 kilobyte of data. So every single packet is 1 kilobyte, and those packets gets transferred sequentially, and all of those go to Google Drive. That will keep my speed also quite good, right? That's the concept of data packets, and that's how you know where your packets have to go. What's next? This can go away. HTTP. HTTP is basically a protocol which is defining how your packets have to go to other places. TLS, let's not talk about TLS, that is its own rabbit hole. It'll take me probably another hour to explain TLS, sorry. Talk about DNS, but before that, let me quickly go get a drink. I'm parched.
Until Siddhant gets back, I want to hear from my audience. Like, how are you feeling? Like, have you learned something new? How's the Josh, guys? Chat.
I'm back. I'm back.
Yeah, back.
The Josh is a lot more active compared to other sessions I've given. I
That's
don't
the
think I've
power of.
Yep. I don't think I've ever had such an active and interactive audience. It's not flattery, it's genuine facts.
Great to have that.
Unless it was something like how to get your first community contribution or how to get your first open source contribution or GSOC or some
Uh,
generic topic like that, right? It's never been so
yeah,
interactive. Not at a technical session.
great going, guys. Let's go.
Uh Supposed to be till 10, right? I might have
Not ne-
to go.
not necessarily. You can continue for
Okay
whatever
then.
time you. Okay.
cool. Just to make sure I don't run out of energy, I'm going to skip a couple of concepts, or rather just explain them in really short ways. Let's talk about DNS. Now, in my browser, I type google.com, right? How does my browser know that I want to go to google.com? It doesn't. My browser frankly doesn't know to go that it has to go to something called as google.com. My browser knows how to go to an IP address. I'm not sure what's Google's IP address, but let's see if this works. Amazing. It actually does take me somewhere. So let's look at this. 8.8.8.8 is an IP address, right? Now I press enter, and what's happening to that? It's turning into something else. It's turning into dns.google. That's basically what your DNS is. Now over here, this is going to give me a really good way to show this to you. Let's say google.com resolve. Now google.com, wait, first here, my data that I want to go to, excuse me. So this IP address right here, which exists, this is Google's IP address, right? If I put this in my browser, it's going to take me to Google. See that? But now I'm not going to remember this whole IP address, right? If I remember this, I remember the IP address of Spotify, of Discord, of Twitter, of Facebook. Take whatever names you want. It's physically impossible for me to remember all of this IP addresses. So instead, we have something called as a DNS name. DNS just stands for domain name resolution or domain name server. It basically maps this name to this IP address. So whenever I type google.com in my browser, it's going to a place called as a DNS server. It's getting the information that this is the IP address which is linked to google.com, and then it is taking me to google.com. Now there are three types of domains: a subdomain, your top level domain, and just your domain name. Now, over here, your top level domain is .com, right? This can be something like .com, .net, .net, .io, .gov. .gov is usually reserved for government stuff. .edu is reserved for school stuff. You cannot buy those domain names. At least I think you cannot buy them on something like GoDaddy or Squarespace. The next part is this: Google. Google is my top level domain. Now, if I have something else, for example, this page, dns.google.com. Over here, this thing, DNS, this is my subdomain. Google is my main domain. DNS is my subdomain. Make sense? All right. So this is actually a pretty good thing. Google has its own DNS resolution thing. If you want to do it in the terminal, I'll show you that as well. You can use a command like nslookup for that. So let's open up a Linux instance. Let's get some actual hands-on and fun stuff. This is Killer Coda, by the way. It's one of the cloud environments, cloud terminals. I have a Linux distro installed, so Sayan, please don't get angry at me for using Killer Coda, but I just haven't set that thing up yet. So let's say that I want to do this thing which I did here. This is called as DNS lookup, by the way. Whenever I type google.com, behind the scenes, my browser is doing the same thing. It's doing a DNS lookup. Over here, I just did the DNS lookup manually. I put in google.com, resolved it, got all of this information. Now, how do I do that in my terminal? Let me just close a couple of tabs because this is getting quite difficult. Okay. In the terminal, let's say I want to find the IP address of google.com. So that's what I'll use ns lookup for. I'll do ns lookup. If I just do enter, nothing really gonna happen because obviously I didn't tell it anything. So ns lookup apparently this isn't typing for some reason. Let me refresh and see. Ronit, I would have been furious at you if you didn't conduct a Linux session as the very first thing.
So I did it right.
Yes, you did. Is this readable or should I zoom in a bit more?
A bit more. Yep, that's
Okay,
good.
cool. So let's do ns lookup google.com. And here I get everything that I want. I get the IP address. Now, if you notice, the IP address which was here and which is over here for Google is different. That's because Google runs on multiple servers. One server of Google will exist somewhere in North America. Not just one, multiple servers actually. They will exist in North America. Some will exist in European continents in different places. Google gets literally billions of requests, right? One single server cannot handle that request. So it distributes all that load among multiple servers. That's why we've gotten a different IP address. If I do it once again, I think it should have the same IP address. It does. If I do it from here, it has a different IP address. If I do it from maybe my own terminal, let's see if I have NSLOOKUP on Windows. Oh, what do you know I do? If I do it here, I'll have a different IP address. Yeah, I have a different IP address. I'll put a screenshot of this in the chat. Okay, again, I explained why these all have different IP addresses, right? Slightly different, but still different. It's because they are all running on different servers, and depending on where I am accessing it from, I go and talk to another server. It all has the same data, has the same functionality, just a different physical server or virtual server. Forget about virtual servers right now. I think you have containers workshop coming up next, right? It'll make more sense over there. Okay, DNS done. Does DNS make sense to everyone? Let me know down in the chat. Awesome. I'm going to skip this internet layer IPv4, IPv6. I already talked about what IP addresses is. The physical layer also we already did cover. So let's talk about the transport layer. That's the only thing which is remaining, to be honest. Wow, I thought I was going to have to cover everything. Apparently, I've already covered stuff earlier without realizing. Nice. So, talking about TCP and UDP. TCP and UDP are just two protocols which control your data flow. We talked about data packets, but how do these data packets actually go and talk to a different device? I'm going to use something very generic. Let's say you have two devices which are represented by these two lines, okay? Zoom in a bit, bring these closer. Okay. Labeling, because without labeling, understanding stuff is tough. Call this A and B. A and B are two different devices. Okay. Now, if A wants to send data to B, first it has to establish a connection with B. Now, it will first send one message to B that, hey, I am computer A. I want to send something to you, to computer B. If computer B listens to this request and it isn't blocked by something like a firewall or something, Computer B will say, hey, yes, I can listen to you. I established a connection with you. Now, A is actually going to send whatever data it wants to send. I mentioned multiple data packets, right? So, that entire flow will happen in this way. Um, A will send a message to B that, hey, I want to send this data packet to you. Tell me if you have received it or not. Once B actually, one sec, let's just properly visualize this. Let me draw a couple more arrows. I have a good way to visualize this. This is a data packet, okay? A wants to send this data packet to B. So A is first going to send one data packet to B. B will receive it. And now B is going to send out a second data packet. This is going to be blue in color. This will send a second data packet, which is basically going to say, hey, I have received your data packet. Send me the next one. So A has its own multiple data packets, right? Let's say it's got a total of 4 data packets. We already sent one data packet. Then A is going to be, A got this message from B that it has received the first data packet, right? Then A will be like, okay, great. I'm going to send you the second data packet. Then the second data packet goes ahead, B receives it, and once again, B sends back a confirmation. And the same thing happens for all of your data packets as well. This is called as TCP, where a connection has to be established between both the devices, between device A and device B. Now, device A can send some message, but if device B doesn't send back a confirmation message that it has gotten it, for device A, it is as good as the packet has been dropped for whatever reason, either a bad internet connection or for whatever reason, the data packet has just not reached. Is it possible to save this note and share at the end? Are you talking about this whole Excali draw diagram? Yep, I can export it and send it in Discord, but a fair bit of warning is going to be messy because there's a lot of stuff over here. I can send it regardless, but it'll just be messy. Coming back to this, if B receives the packet but doesn't send back a confirmation message, A is going to consider that as the packet has not been sent at all. So in that case, A will send the exact same data packet again. Now it could be that B receives duplicates. So these data packets also have numbering information inside them. In binary again, the data packet has got now 3 things that you know about. Once more, what there are in data packets. I'm about to tell that itself. The data packet has got 3 things within it. Let's say that you upload a video file, right? And all these 4 data packets belong to that one single video file. These data packets are going to contain a couple of things. Number 1, the data of the video itself. The data of the video is going to be split across these 4 packets. Second thing is going to be numbering. That this has the first chunk of data for this video file. This packet has got the second chunk of data. This has got the third chunk, and this has got the fourth chunk of data for this overall video file. Okay. And the third thing which all of these packets are going to have is the source and destination IP address. So they're going to have the address of device A as the source, and then they're going to have the destination of B as well as the other source. Make sense? That's basically what TCP is. I know I rushed through it, so let me know down in the chat if it's clear or not. Ami, is it clear like what's inside the data packets? I just mentioned that. Okay, awesome. It's fine if you haven't understood TCP/IP. sorry, just TCP protocol. This thing is a little um, difficult to understand the first time you try it. So it's, if you're just getting understanding a little bit fragments here and there, that's totally fine. But just let me know if it's making it or not, making sense or not. I have no idea what is ARQ. What is ARQ? A movie? Shreyo, please explain what's ARQ. I have no idea what that is. So A is sending some data file to B. So what is B sending back to A? B is sending back a confirmation that, hey, I have received the data packet. Let's say that this data packet was called number 1, right? So B has to send back a confirmation to A that, hey, I have received data packet number 1. Please go ahead and send me the next data packet. Make sense? Ah, cool. Okay. That's basically your TCP thing. Kind of like a handshake. A handshake is a concept in TCP itself, to be honest. The TCP handshake is what's used for establishing a connection. Let me just Google a diagram because I'm feeling lazy to draw. Handshake. Let's use this thing. The exact same diagram I showed you, right? This sends the actual data packet. Your server sends a confirmation that, hey, the data packet is received. Then the client or device A sends the same data packet again. Now this SYN plus ACK, I'm not totally sure about these terms. I heard about these recently itself. I don't remember the full form, to be very frank. Let's see what it is. SYN TCP handshake. Mm, Just want to know about the full form. Synchronized sequence number. Okay. Does this have the full thing? Okay, yeah. We have that thing over here. Used to initiate established connection. So again, this is just starting the whole connection. Another synchronization plus ek is acknowledgement, like Pratik said. Then you have another acknowledgement going that, okay, I'm sending you the other packet. All right. Wait, this thing had another thing. There's also the fin thing. Again, used to just terminate. So once all of your data packets have been sent and received, you'll just terminate the connection. You don't want to leave the connection open, right? It will just lead to security errors. So this is the whole TCP thing. UDP is similar, but the only difference with UDP is you don't get any sort of acknowledgement. So A will just send the data, just send the data, just send the data. And B might receive it, might not receive it. We don't really care about that. UDP, the use cases for UDP protocol is more with video conferencing. So right now in Discord, for example, I'm talking to you with UDP. My audio packets might be dropping at some places, and that you're hearing as some audio cracks, audio glitches as well. Same thing happens with video calls as well, Zoom calls, Google Meet calls. When your video is enabled, your packets are going through, but they're going with UDP. There isn't a established connection that the packets are going to be received. The packets might drop as well. So if you're trying to send data to Google Drive, you'd prefer TCP because this is going to not lose any of the data. But if you're doing a video conference or an audio call, you'd use UDP because if you establish a TCP connection, firstly, in terms of performance, that would take too much time. Secondly, I say something, it might take 10 seconds to reach you, depending on internet connectivity. So that's why UDP is preferred over here. Shreya just sent some really nice diagrams for TCP and UDP. Do check those out. Yeah, I think that's it. I think we can, let's just go ahead and play a little bit with net tools. So if you have an Linux based operating system, you can go ahead and do these things as well, which I'm doing. First thing which you want to now, a little earlier in the chat, Sayan as well put in a command called trace route. Trace route is basically telling you what route does a packet take. How is the packet getting routed to reach its final destination? We'll see that. But first thing you need to know is whatever operating system you install, by default, it might not have any of these networking related tools. So you want to install that with something called as net tools. So since this is a Debian based distro, it will exist in this package called as net tools. Let's go ahead and install it. And if you want to know what all tools come with net tools, you can check out this website. I'll dump it in the chat as well. Net tools is basically what do you call it? A collection of packages. This is what all the packages are which are existing within net tools. And net tools by itself is a collection of all these different packages. So let's first go over here. First, I want to see what all devices are connected to this particular computer. Now, this is a VM, so things might be a little different, but I can just say IP link, and IP link is showing me what all the devices are connected. Over here, there's a loopback thing. Loopback is a special type of device which is a part of the kernel. So this is software defined. Then next you have link ether. This is, I'm assuming, whatever the virtual Ethernet connection is for this particular instance that I'm running. But if you try this on your own local thing, you might see WLAN 0 or WLAN 1 or something slightly different. You might see ETH0, ETH0. That means that you're connected with a wired connection. WLAN will show up when you're on a Wi-Fi connection, as far as I know. And the IP command is actually kind of fun. Let me just do a help so I know what I'm looking for. Root, yes. Let's look at a routing table or routing table. How do you pronounce it, by the way? Do you pronounce it as root or route? Let me know in the chat. Route. You know, even at home, for like driving route, I always call it as route. So my folks get really annoyed. Route. Okay, I'm just going to go ahead and call it route. Sorry for triggering some people. So if I do IP route, I can see that these are a couple of routes which I have. These are all my routing tables. Second thing I do is I type just route. Now this is showing me an actual routing table. This is the same thing as the IP route, but this just formats it a lot better. Now I'm going to talk to you about this. Destination default, which means it's my router. This is basically the gate. We talked about gateways in Excalibur, right? Do you folks remember what is a gateway? I talked about router being a gateway, right? Gateway as in it just allows you to talk to the outside world. Make sense? The same thing you have here in your root table. This routing table is in your kernel, by the way. This is not your router's routing table. This is your operating system routing table, what exists in the kernel. You can change this as well using the IP root command. Not doing that here because that will again be too much time taken. So default basically is using this IP, whatever device is at this IP address as its routing table. This gen mask is something called as a subnet mask. A subnet mask comes into the picture when you're playing around with private and public networks. Then metrics, flags, reference, use, no need to bother with this. iFace is basically an interface. Now ENP1S0, this could be some sort of a physical device. But in this case, I'm just assuming this is a virtual device. Docker is, well, Docker. I don't know. You'll learn more about Docker in next week's session. So this is basically the routing table. There is also one thing called as ARP table. Let's see if this comes. All right. ARP table is basically a list of all the physical IP addresses. I didn't talk about physical IP address, but every single device basically has something called as a MAC address. This MAC address is basically your physical address. Every device has a physical address. This particular instance has one particular physical address. It looks something like this. Let me show you what physical address looks like. Yeah, this is what a MAC address basically looks like. Where's a good? Yep, this is a good one. So you basically have a couple of numbers this way, and that shows you your MAC address or physical IP address. Let's come back here. So ARP tables is just a list of all of those physical IP addresses. Let's see what next to do. Trace root. Do I have that? Okay. So then trace root is a separate package itself. Install trace root. Trace root is actually a newer version of an existing tool. I don't remember what the older version is called. I think it was called something net something, I think. Net trace or something. But trace route is basically going to show us the entire route a packet is taking to reach the destination. So I'm going to run a trace route for google.com. Okay, couple of different entries. Let's look at it. This thing is my router, whatever it is. After going to my router, it goes to this second thing, which I'm assuming is a server of Killer Coda. Then it goes to somewhere else, then it goes to somewhere else, another somewhere else, and it's basically hopping so many times before it finally reaches the destination of Google. So traceroute is quite a useful tool to visualize the entire path it's taking. Yes, if you work as a network engineer, you're going to have to get used to all of these numbers. But yeah, this is what traceroute does. It's showing you all the hops that the packet is making. If I'm not mistaken, this is most likely an AWS server. I recognize the naming convention. I'm pretty sure this is somewhere running on AWS cloud. Or Hetzner, no idea. What else can we do? Curl. Should we go ahead with curl? Okay, sure. One of the most important tools which you'll have in your arsenal is curl. Curl basically is a versatile tool. It allows you to do a lot of HTTP requests. Now there are four main HTTP requests: get, post, delete, and patch. Not going into much details about this. If you're in backend development, you'll have a better idea about this than me. But get basically means that you're fetching some information from an endpoint. In this case, the endpoint is google.com. I enter this. This is what I get. This is the output which I get by pinging Google, by going to google.com, by curling google.com. Now I can do post as well. Post means that I'm just sending some information over there. I can do patch, that is updating. I can do delete, which is deleting. One more useful tool, ping. So ping basically helps you figure out whether you're able to talk to a particular server, a particular endpoint or not. If I do ping google.com, it's giving me responses, and that means that I'm able to talk to google.com. Now 8 packets transmitted, 8 packets received, zero packet loss, and this is how much time it took for that entire process to happen. So it's quite useful for debugging all of those things to see if you're able to talk or not. Story time. I was actually trying. So my home, in my house, my entire routing setup is a little complicated, right? I'll show you how it is. So this is my ISP. My ISP sends me one connection, okay? Now this connection is attached to three physical devices. One, two, three, I believe. So one of them is my desktop, another one is my printer, and this one is, I'm not actually sure what this is. Let's just consider this as wireless, so I'm getting rid of this. Now this is one network, okay? My network is a little complicated. I have a second router in my house, and my first router is connected to my second router. So my second router basically acts as an access point, and this router is then connected to my laptop. And I, back then I had a old PC which I used as a server as well. So let's put that in here as well. So this is one router, it has its own thing. If I remember my numbers correctly, this whole range was running on 192.168.0.1. This first set of network was running on this IP range, and the second one on my side, it was running on a different range. It was running on .1.1. Can I call it an extender? It's not exactly an extender. It sort of did work like an extender, but not exactly. It wasn't a Wi-Fi extender. Rather, there's a lot of distance between my devices, to be honest. So this exists on one side of the house. This is on a completely separate side of the house. I couldn't pull any wires from here even if I wanted to. So I just took one single wire, brought it to here, and created this as my own separate network. This has its own devices. Now I was trying to ping from my laptop to my desktop, and for the longest time that connection wasn't happening. So for that I had to do a lot of things. I had to do something like IP route gateway, set up this device as a gateway, go into a configuration of my router, and within it set this thing as its other gateway, and then finally after a lot of jankiness I was able to reach there. And all of it I was able to do thanks to ping and curl. That's how I knew that uh, my connection is actually established. I'm not sure if we looked at NS lookup or not, but NS lookup is just a DNS lookup. I showed you this website, right? Like I put in google.com and it showed me this whole information. The same thing I can do over here. I put in google.com and it gives me all the information of google.com. What else do we have? Dig, I guess. Yep, let's go for dig. So let's do dig google.com. Now dig basically tells me all the information allocated to this domain name of google.com. Um, so it's basically telling me that google.com has all of this information. This is a little confusing for me as well, but basically dig is supposed to tell me that google.com is a domain which is owned by such and such IP address and similar sort of information. That's what dig is used for. And yeah, I think I've covered up pretty much all of the basic commands and concepts which you'll use for networking throughout either a DevOps career or a network engineer career. Heck, you would use the same concepts even for backend stuff. So yeah, if I've missed some commands that you might know of, just drop that down in the comments because there are honestly a lot. And if all the concepts are clear and nobody's finding anything which I missed or you folks didn't understand, I guess we can call it ends of the session. So yeah, let's call it Q&A time or just general chit chat time. So feel free to come up on stage or just drop some questions in the chat and we can take that up.
And followed by this, we will have a quick quiz. We have set up 15 questions on which, on the same topic. So stay tuned for that as well.
Ooh, quiz. What happened at the end? Nothing much. We just looked at a few practical commands.
In case you missed out on that, you will have the recording, and you can actually reiterate on the stuff. No issues. Awesome. So, yeah, over to you, Monal. I think he's done from his side.
Yep, I'm done.
Okay, folks, now we have some interesting stuff coming up. The quiz, which we all wait for. There are chances of swags. Last session also we got three winners. Now we will have three more winners. So I would like to ask Nimesh to give the link of the quiz, please.
Can I
And
participate?
special thanks to Siddhant. Yeah, but you will answer most of them correctly. So, you are the educator. No comments on that.
Cool, cool.
Yeah,
Yeah,
but
well, that will be considered.
honestly, thanks for your inputs. We learned a lot from this session, and the crowd is also very, very happy. They were also responsive, as you said that it was one of the most interactive crowds you have ever met.
Sleeping, I guess.
Anyways, we can start off, I guess.
Okay, guys, the quiz is live. Let's do this. Okay, I guess folks have studied. They listened to the session. The full form has it all, guys. We need the correct answer for this. Nice. Okay. Okay. Not bad. Nimesh, we are not going to give you the swags. Even if you win, you have all the answers already. First one is invalid. Nimesh, we are not giving you any swags.
Wait, who's not getting any swags?
He's a part of the organizing team and he has all the answers, so he's not valid for having swags. But he's still
So,
part.
so based on what you're telling me, if I join in from my second identity, you wouldn't know it's me and I'd get swags. Hmm.
Now you have to fill up a form which will mention your name and address. So yeah, we will actually catch you doing that.
I mean, I can put my second name and you still don't know my address.
All right, I have it. I have the speaker's ID, address, everything. If I remember correctly.
Do you? I don't think so. Did that form have that? I don't think it had the address.
Okay, maybe. I don't know.
Siddhant trying to steal the swags of deserving candidates. Not happening.
Not happening. Not happening. Definitely not happening. He's the one to
Good,
provide one.
good, good. CHCF Hooghly has got good organizers.
Our pleasure. Actually, I talked to Kaivalya as well. If he
Hmm.
can join in, but he seems to be busy for some reason. So yeah. Is Sanyukta screen buffering for every individual or it's just me on my network?
Not really buffering. I can see the screen properly.
Okay, this is my issue then.
नाइस चलो इस क्वेश्चन पे 1 घंटा हमने दिया था लोगों ने सुना है अच्छी बात है
1 घंटा?
उस क्वेश्चन पे उस स्पेसिफिक क्वेश्चन पे
अरे ये चीजें तो मैंने कवर किए भी नहीं थे.
नहीं फिजिकल डिवाइसेस पे हमने कवर किए थे
टोपोलॉजी नहीं किए थे कवर.
ओके आई गेस फिर मेरा स्क्रीन लैग कर रहा है आई वाज टॉकिंग अबाउट द फिजिकल डिवाइसेस
हाँ. हाँ, फिजिकल डिवाइसेस लिटरली 1 घंटा. बट टोपोलॉजी वी डिडंट टॉक अबाउट.
नो प्रॉब्लम वी हैव सम इंटेलिजेंट folks here
चलो बच गए. It seems that Sayan is not among the participants. Other people actually have a chance for swags.
How many questions are left? It's actually not visible from my side, so I don't know
11 out of
where we
50.
are.
I
Okay,
I guess 4 questions left
okay, okay.
Okay. Can you show us the leaderboards? Got to see who's winning.
Hmm, hold on.
लेट्स सी लास्ट तक कौन था। इस क्वेश्चन का आंसर वही दे पाएंगे जो लास्ट तक थे। नेटवर्क लेयर।
Seems to be
Okay,
Sanyukta
not
is,
a lot of people.
and I can't at the same time.
I see question number 13 on screen right now.
Yes, I can as well. There's a difference. No, this is covered, guys.
Yeah, this one is actually
Yes.
covered.
चलो लोगों ने सुना है।
Yeah.
And the second last question we have.
ये VPN देखते मुझे पता चला, अरे वो याद आ गया मुझे. Actually, what happened? Like, I have been to China, okay, and there's a great firewall of China, and nothing works over there. Literally nothing. No Google,
Hmm.
nothing. So like I had to survive on VPN, जो कि आधा टाइम काम भी नहीं करता. It's
तुम
very stressful over there.
अच्छा, you had gone to China OSS summit?
क्यूबकॉन.
हाँ, तो वही क्यूबकॉन प्लस OSS summit.
हाँ हाँ हाँ. तो ऋतिक भी गया था. Like,
ऋतिक, आयुष, इंडिया से 3 या 4 लोग गए थे आई थिंक.
yep, I had the returning flight with Ayush.
Nice. I had my first international conference talk accepted, but I couldn't go cause funding.
That's the issue. Like, same for me in, like, KubeCon Paris. Like,
Hmm.
stuffs are very difficult.
KubeCon Paris at least gives you a fund. This conference didn't give a fund, and my company didn't wasn't willing to sponsor.
Now, with that being said, we have the final results, I guess.
Nimesh valid for swags gets 14 points. Interesting.
He
No,
is
he
not valid for
doesn't.
swags.
He's not valid for five.
The eligible candidate is Rajdeep Kundu. The second eligible person, it's not Shaumadip because he has already won a swag in the last one, I guess. I believe, if I'm not wrong. So we will provide uh, like opportunity to the others. So the fourth one is Pratik. So we will consider him the second. And the third, but not the least, was is Bishwarup. Okay. So Rajdeep, Pratik, and Vishwarup, congratulations! You are the winners for this quiz. Your experience, like, according to him, it was his first ever workshop like this. So Siddhant, your thoughts?
My thoughts are I actually need to properly prepare for a workshop next time. At least in terms of audience, it was amazing. I frankly wasn't expecting this much of an active audience.
I'm so happy to, like, have such audience who are interactive, who are actually interested to learn about networking and the concepts, so that they can land up into the realm of DevOps and cloud native. So, like, that's awesome actually. It was also, like, great to host you. Like, the session was interactive, people enjoyed, and thank you for coming and like adding value to cloud natively.
Thanks for having me.
All right, then, good night, Siddhant. It was really, really great to have you over here.
All right.
Thank you.
Thanks, Ronit.
All right.
Just a question. Is it pronounced Ronit
Yeah,
or is it Rohit?
it's Ronit.
Ronit, okay.
Yeah.
Because I think I read your name as Rohit on LinkedIn, so
Yes, I never, like, corrected you because I thought that it's all right to like pronounce anything that is comfortable to you. So yeah.
No, no. You should correct it, to be honest.
Okay, next time I will.
Yeah. All right then, everyone. Thanks for
All
joining
right.
today, and good night.
Okay. Bye bye. Good night, guys. Thank you everyone for joining, and let's meet in the next session of Kate Smashers. Till then, goodbye, good night, signing off. Bye bye.